Okay. Can everyone hear me? Just a test of my mic. Awesome, perfect. Okay. Let's just check the video's working. Hello, hello. How's everyone doing? Video quality looks okay. You might have to run it at a lower quality if your internet connection's not quite as good, but hopefully not quite potatoes. So let me know how the video and the audio looks and sounds. We'll give it a few more minutes to see if anyone else pops in before we'll get started. Awesome. All right, let's transition to getting started. So yeah, how's everyone doing? How's your studying and weekend going? No problem. My pleasure doing this. So the plan more or less right now is, so because of the time I was able to devote today to the things I was doing, I'm going to work off of the practice exam that is currently posted. This is one that I made for his class in summer 2018. So we're going to work off of that, but what I'm going to do is I'm going to make sure to review the concepts as we kind of go through them, and if there's any holes that are, there's concepts that you see that are missing in this, we'll touch on those. So like for instance, you might notice, okay, well there's nothing on RC circuits in here. What I'll do is I'll insert some stuff to kind of cover those topics. If you have any particular topics that you would like to go over, throw them into the chat now or anytime. Just request any topic that you want to see a little bit more of. Any questions you have, toss them to the chat. Just let me know about anything. Are there any general questions before we get started? I'll also be relying a lot on your feedback through the chat. Hopefully at least one person types something in chat every now and then to give me feedback. Question, are you still going to post another practice exam? That is correct. What I'm going to do is after the live stream tonight, when I do have a gap of time, I will be making another practice exam, and I will be posting that online for you to take a look at. I'm going to do my very best to make sure it goes up tonight because I want to give you more than enough time to at least look over at least the solutions by tomorrow. And what will happen is you'll have that available before tomorrow. And if you manage to find time to come out to the review session in person, then we will be going over that during the review session in person. So I'll be sure to get that up as soon as possible tonight. And hopefully it'll include actually more of the stuff that's missing in this practice exam. Another question, can you go over the difference between series and parallel circuits and how to differentiate them? Oh, absolutely. There are a couple of problems in here that I specifically designed to kind of, I don't want to say trick you, but I want you to catch where your mistakes are going to be. So a couple of the problems on here with the circuits are going to kind of show you the weak points where a lot of people fail with circuits, which is trying to differentiate between the two. So we'll be sure to definitely make sure we cover those. That'll actually be all the way down in questions 17 and 19. Yeah, so these circuits, 17, 19, they're very basic, but they will help you to realize what actually makes something series and what actually makes something in parallel. And we'll do that with resistors and capacitors. We'll do even more examples with this beyond what's on this practice exam, so I'll make sure that you have a better understanding of that for sure. Any other quick questions before we get started? Okay. There's also going to be, you'll notice there's a slight delay between when I actually talk and when it actually goes through to you. So if there's about 5 to 10 seconds of lag between my actions, it's because of that lag. So, all right. So let's take a look at this first one. And what I'll do is I'll go back and forth between the whiteboard as necessary to work out anything. First one is very, very straightforward. This is just a way of saying, do you know what this is? So for number one, a physical property associated with protons and electrons is known as charge, and it has a standard SI unit of coulombs. You ought to know how to spell it out, simply because a lot of times if we ask you to like, okay, what's the unit of this? We can't just say, you know, it's okay to write C, because what does that mean? Is it Celsius or is it coulombs? So you should probably know how to spell that out. So charge as in coulombs. Number two, so we have a common isotope that is found, radon, in which the nucleus consists of 86 protons and 136 neutrons. Calculate the total amount of charge in standard SI units, in other words, coulombs, in the nucleus. So what we're going to do here is to calculate the total charge. Hello again. Total charge for number two. Okay. So remember that the variable that we use a lot for charge is Q, so I'll be using Q to indicate the amount of charge. So the charge total, so if you have a bunch of, protons, electrons, and neutrons, we could take all of those particles and we could add all their charges together. So for instance, I could say that the total charge could be the charge of a bunch of protons. Let's actually just call it Q plus to abbreviate that. Plus the charge of a bunch of electrons, plus the charge of a bunch of neutrons. Okay, but conceptually, there's a couple of things you should remember. Right, so number one, for protons, okay, they have a charge equal to positive, let's call this E. Okay, so E is some constant. It's either called the elementary constant, or it's called, or I'm sorry, the elementary charge, or the electron charge. And then for our electrons, the charge is minus the value of E. And that value is a given constant, so when you have your formula sheet, you'll have all the formulas that we covered, and you'll have all the constants, so you don't need to remember what these things are. Hopefully you will have used it enough that it's kind of sort of ingrained, but the value of E is 1.6 times 10 to the minus 19th coulombs. Okay, so again, that's a given constant. So protons have positive that value, and electrons have negative that same exact value. If we ask you what's the mass of a proton or electron, well, that's drastically different. The only thing that's the same in terms of size is the charge. Okay. And then we know that neutrons, the charge is 0. Okay, so no charge on neutrons. Now, to get this right here, to get the total charge, I wrote out that it's the charge of all of our protons, all of our electrons, and all the neutrons, just to be thorough, but technically there's no charge on the neutrons. Okay, so we're only going to take a look at the protons and the electrons. In this case, because we're only asking to calculate the charge of the nucleus, which is made up of protons and electrons, I specifically say that it consists of 86 protons and 136 neutrons. What this means is the total charge is only the charge of those 86 protons. So Q total equals 86 proton charges, which is just 86 times the value of E. So we have 86 times 1.6 times 10 to the minus 19th coulombs. So the total charge is, and let's just calculate that. Make sure you bring a calculator that you're comfortable with. I know some people like to rent calculators. It might work short term, but you want to definitely get one long term that you get very comfortable with using, so that you could just easily do things without hesitation. So that'll save you time when you, at least on the exam. 86 times 1.6 times 10 to the minus 19th gives you a total charge of 1.38 times 10 to the minus 17th. Standard units are coulombs. Okay, so this is the total charge in the nucleus in problem 2. So let me know if you have any questions about this. I'll give you a little bit of time to take a look at this, and then we'll move on in like 30 seconds if you don't have any questions. Okay, let's take a look at number 3. Doesn't look like anybody has any questions. So number 3, two like charges will, so if they're the same kind of charge or like charges, they will repel each other. and two unlike charges will attract. So in other words, like charges would be, for instance, positive, positive, and unlike charges would be negative, positive. So that's just conceptual. Number 4, if two charges are placed near each other and Q2 has twice as much charge as Q1, how much force will Q2 feel compared to Q1? So it's a very, I guess I want to say it is an easy question, but it tricks a lot of people based on the wording, depending how it's worded. We say that one charge has twice as much charge as the other, but it misleads you into thinking, oh, well, the force has to be twice as much as the other. Well, no, because let's say if I draw this out real quick. So when we draw out the picture for our two charges, it's just, okay, so we have two charges that interact with each other. Doesn't really matter so much if they're positive or negative. It's just one has twice as much charge as the other. So let's just say that we have a positive charge and a positive charge. We have that this is Q1. Let's call this one Q1. Let's call this one Q2. And we know that Q1, let's just say, has a charge of Q, where Q is just some number. It's not given, but whatever number that is. Q2 has 2 times Q, indicating it has twice as much charge. Now, when you complete the diagram, you would basically say, okay, well, these two charges would want to repel from each other because they're the same kind of charge or they're like charges. So the way to do that precisely is to draw this line that connects the two charges, put a line through it, almost like you're making like a shish kebab out of charges. So, but what would happen is the forces would always reside along that line. Whether if the forces point along the line towards or along the line away, it's always going to be along that line. So in this case, because we know they repel from each other, they're going to point away from each other. So the force points that way, and the force points that way. But if I were to say, okay, well, how much force does it feel, which is what we're being asked here. How much force in other words, the magnitude of the force implies Coulomb's law. Okay. And Coulomb's law, we have that the electric force equals K. I'm going to call it generically capital Q and lowercase q, and then over r squared. A lot of times they'll write Q1 and Q2 in the formula. I like to just leave it general just in case we have more than 2 charges. But nonetheless, you have 2 charges in there. Now, the thing is that this will allow you to calculate the force on either of the charges. But you'll notice that regardless of which charge you ask about, you're going to be plugging the same charges into the formula anyway. So what happens is you get the same force on Q1 as you do on Q2. You get equal force, opposite direction, equal and opposite. That's just Newton's third law. So regardless of the sizes of the charges, if you're asking about the force on either one compared to each other, well, they're the same size, equal and opposite. So the force on charge 2 is the same as the force on charge 1, regardless. Let me know if you have any questions on that. Or if you're good, let me know in the chat, and then we'll move on to the next one. So how does the formula relate to this problem if we can use Newton's third law? Think of it as you have at least 2 different ways to explain the same thing. Whether if you choose to use Newton's third law to explain this, equal and opposite reaction, or you choose to use Coulomb's law to show that regardless which charge you're questioning, the force is going to be the same, you're still going to reach the same conclusion. It's just basically 2 ways of approaching the same answer. So you could do either or in the end. All right, let's take a look at the next one. So number 5. If two identical charges are placed near each other, so identical implying that they are the same charge, they have the same mass, any properties pertaining to the charge is completely identical. If they're placed near each other and the distance between them is doubled, so we take some distance between them and that'll be our initial situation, and we'll move them further apart to some final picture. How much force is felt by either charge compared to before? So now to kind of boil this down a little bit. So what we're going to do is we're going to take two charges. Let me draw two separate pictures to indicate what's kind of happening. Because in the previous problem, what we were doing is we were comparing what happens to one charge versus what happens to the other. And we said it was the same thing in terms of the force. But here what we're doing is we're comparing two separate situations. So in situation A, let's call it, this is going to be our initial, okay, we have two charges. They could be any kind of charge, so as long as they're identical, because the key with this was that they were identical. So whatever charge this one has, this also has the same charge. So we have some charge, let's just call it Q, and this one's also Q, so they're the same. Now, there's going to be some distance separating those two. Okay, so here's that direct line between the two, and the distance from there to there is generically called R. Okay. In this case, let's call it R, maybe let's say I for initial, and we're going to compare it to what happens final. So when we change this picture to our final, okay, what we're going to do is we're going to bring these charges further apart from each other, so it's twice the distance now. So we have our charges Q and Q because they're identical, and now that distance that separates them, you could call it R final generically. However, we know that this distance is 2 times the initial distance. So we double the distance between the two. And the question is, what is the force felt on either one in this situation compared to this situation? So if I were to say that these feel some force F in this situation, would they feel the same force F in this situation? So if this was 100 newtons, is it still going to feel 100 newtons of force? Well, we know that in this one you do have to use Coulomb's law. So we know that the force has a dependence on the charges, the two charges, and the distance squared. 1 over the distance squared, also called the inverse square law. So what we're going to do is, I don't really care so much about the rest of the equation. The one thing I really care about is the fact that the distance changed. So how we handle comparing one situation to another is by using something called a proportionality. This is not something that's taught in the class, and it's not maybe something you've seen before. It's a very simple idea. It really helps you to boil things down, because we're going to ask you a lot of questions that deal with comparing one situation to another. So this is a very, very simple and powerful tool. So all you're going to do with this proportionality is you take the equation. Okay, so I want to talk about the force, so I say the force. But instead of writing an equal sign, you write this little fishy symbol. Looks like a little fish or like a Greek alpha. But what it means is ignore things that remain constant. So if it does not change from one situation to the other, ignore it, leave it out. So in other words, these two charges, they never changed in that situation compared to the other. They stayed the same amount of charge. So I do not write the charges at all. Coulomb's constant, by definition, is a constant. It doesn't change, so we ignore it. The only thing that does change is the distance. So we write 1 over the distance squared. You write the entire term, and you write it where it is in the formula. So the point of this is to say that the force varies with 1 over the distance squared. So when you use a proportionality, the only thing you do care about is by how much it changed. So when you plug in, the only thing you plug into the distance is by how much it changed by. So did it double, did it cut in half, or did it triple? In this case, that factor is a factor of 2 because it doubled. So all you do is you write 2, you square it, and you get 1/4. So in other words, the forces in this final situation is actually 1/4 the force in that picture because you doubled the distance. And the same thing on this charge. It's still 1/4 the force. So the force final equals 1/4 the force initial. That's what this is saying. So just by simply knowing that factor of 2 that you double the distance, all you do is you plug it into this and it gives you 1/4. You're done. Okay. So we'll kind of utilize this in the future with other formulas, but you use this anywhere you want to compare one thing to another and it gets you the answer real quickly. So if you have any questions on this, let me know and we'll move on in like about 30 seconds. Question, where can I find the practice exam at? It should be on Canvas. If you go to the home page on Canvas with all the uploads, it should be halfway down the page. There's a whole section that has all the practice exams. So you should be able to find it there. Any other questions on this problem? So the answer to this one is D. So 4 times less force will be the answer for this one. Okay, so let's take a look at number 6. Everyone seems good. Okay. The proton of a hydrogen atom and the electron in the orbital around it are separated by a microscopically small distance. The force that the electron feels due to the proton is 8.2 times 10 to the minus 8th newtons. Calculate the distance that separates the proton nucleus and the electron. So this one's just pretty straightforward. You just do a calculation, but it just implies you just need to manipulate the formula around, given that you know what it is. So with this one, I realize that there's at least 19 people tuned into this, so thank you all for tuning into this. It's pretty awesome that you all took the time to do this with me. It's fun for me too, so I don't feel like you're taking up my time. I love doing what I do. So for this one, 6. So we have 2 charges. Here's a proton and the electron given in the problem. Okay, so we know it's a proton and an electron. So proton. And we know the proton's charge. Let's call this proton Q1. We know it's just positive, the value of E. And for the electron, we know it's just negative, that same value, which is given on a formula sheet. Okay, so Q2 is just negative the value of E. Okay. So we know their charges because it's stated that it's a proton and an electron. We know the force that acts on these. So the force that the electron feels due to the proton, which actually doesn't really matter. I could tell you it's the force on the proton instead of the electron. We know that the forces are just equal and opposite. The force either way is 8.2 times 10 to the minus 8 newtons on either of those particles. Now, we know that the equation that tells us the force between 2 point charges is Coulomb's law. So we know that it's F equals K. In this case, we're calling it Q1 and Q2 divided by some distance squared. We're going to solve for the distance in this problem. So we're going to do a couple of things. So we're going to take the r squared in the bottom, and we're going to move it over to there by multiplying. And we're going to trade places with the force, and we're going to divide it down into the denominator. So r squared equals K, Q1, Q2. The K out front is implied that it's in the numerator when you write it out front. All of this divided by F. And then to isolate r, we just need to get rid of the square, so we're going to square root both sides. So therefore, r is equal to the square root of K, Q1, Q2 over the force. Okay. Most common mistake here will be either forgetting to convert your units over if needed, or forgetting to square root. That's another common one. So also squaring. I cannot tell you the number of times that people forget to square things, whether if they just don't write it or if they just forget to put it in the calculator. So every single time, don't forget to use that square. I'm going to take the square root of the value of K, which is another given constant. It's Coulomb's constant, 8.99, 10 to the 9th Newton meters squared per Coulomb squared. Q1 and Q2 are both the same amount of charge, just plus and minus, but remember that when you use Coulomb's law, we only use it with the magnitude, meaning that we only care about how big it is, positively. We're not going to plug in any negative numbers because we take care of the direction separately if we need to. So we're only going to take the absolute value of everything we do. So we have 1.6, 10 to the minus 19th coulombs for the proton, and the same value for the electron. Okay. All of this divided by the force, which is given to be 8.2, 10 to the minus 8th newtons. Okay. So we're going to plug and chug all of this, and we're just going to get an answer for that, and we'll get R equals. So quickly, we'll get 8.2, 10 to the minus 8th. That's in the bottom, and then multiply across the top. That times that times that. Okay, so we get an answer in the square root, and then we square root it all. Okay, so the answer that I get, if any of you would like to confirm to make sure that I'm giving you the right answer, 5.30 when you round it, 10 to the minus 11th. I actually believe that is the correct answer because I designed this problem to use the distance between the proton and the electron. So this should probably be the correct answer, but let me know. Let me know if you have any questions on this, and we'll move on. Ooh, awesome, you found it. Cool. Glad you found the practice exam. Okay, awesome. Makes sense to you. Cool. All right. Let's take a look at the next one. Okay, 7 is just conceptual. All point charges emit an electric field all around them, which points, now if you read this in every direction for positive charges, it's away in every direction for positive charges, and points toward in every direction for negative charges, or any equivalent wording to that. So remembering that if you draw out, here, let me sketch it real quick. If you have some positive charge, okay, no matter what point around it you pick, okay, if you pick this point or that point, this point, this point, or that point, doesn't matter. The electric field will always point directly away from it. So if you would imagine that there would be like this line that connects to every point like this, if you were to imagine that, you don't have to draw that, but it might help you to draw it. The electric field would point along that line and away from the charge. in every single direction, no matter what point you pick. Okay? And conceptually, what you want to remember about the electric field, and this is something that a lot of people get confused about, the electric field is something that is present with only one charge being there. You do not need another charge to be present anywhere else, because when you use like Coulomb's law to calculate the force between two charges, well, you need two charges to do that. In order for a charge to feel a force, you would need to have another charge present. So an electric field is something that's going to exist in the space around a single charge regardless. Okay? So a lot of times we have problems where we say, calculate the electric field at this point. There is nothing at that point. It's just an electric field there. There's no charge actually present there. You can stick a charge onto that point, but whether if the charge is there or not, there will be an electric field there, so as long as you have that single source charge. Okay? And then, of course, quickly recalling that for negative charges, you could say exactly the same thing for its electric field. It just rather points inwards towards it from every single possible direction. Okay? Now, let's take a look at 8. And this is where we're going to take some of that knowledge and actually apply it. So for 8 and 9, actually, we're going to use this diagram here. Oops, change that over. Okay. So on this diagram, we have this grid that marks out a coordinate system. We have a point P1 here and a point P2 over here. Okay. There is nothing necessarily at those points. Those could be, again, empty points in space, but we are saying that there is an electric field that's measured at those empty points in space. Okay. So call those E1 and E2. First thing we're going to determine is what is the location, in other words, what's the coordinate x comma y of the charge in the figure above. So for this one, if we know that the electric field, let's say at point P1, this electric field points diagonally down to the right, okay? We know that it can mean one of two things based off of what I just told you from question number 7, okay? We know that all point charges emit an electric field around them, which either points toward or away, depending on the kind of charge. So given that knowledge, we could say that this electric field E1 either points away from a charge that's somewhere over here in the upper left-hand corner, or it points toward a charge which is somewhere down in, to the right, somewhere over here. Now, you would have to guess or flip a coin with just that knowledge alone, but that's what this other point is for. Usually when you have more than one point of interest, you can use the information from both points together to actually conclude what the answer is. So in this case, well, we know that for P1, the charge cannot possibly be in the upper left-hand corner, because if it was, then it wouldn't make sense for the electric field at P2 to be pointing, somewhere that's obviously not in that direction. So based on the fact that E2 points, down to the left and P1 pointing down and to the right, you should be able to conclude that the charge is somewhere in the vicinity over here. And in fact, you can do this precisely because, for instance, E1 goes over 1, down 1, over 1, down 1. That's the slope. So if you just continue over 1, down 1, over 1, down 1, and you do the same thing for P2, which is also conveniently just over 1, down 1, you can actually kind of staircase it over until they cross, and they should cross at -1, -1. So if you just draw the lines and then find where the two lines intersect, they'll intersect at -1, -1. So that's the location of the charge. Now, in the second question to this, so question number 9, what kind of charge is at this location? Well, now that you know its location, and given that you know these electric fields are pointing towards that location, you would know that it has to be a negative charge because all electric field lines point towards it. So -1, -1, and it's a negative charge. Let me know if there's any questions on that before we move on to 10. All right, looks good so far. All right, let's take a look at 10. If the magnitude of the electric field is given 100 newtons per coulomb at a distance of 10 millimeters away from a point charge, how much charge is there? Okay, so for this one, given that we know that there is a point charge, we know that there is an electric field value given and a distance. The equation that best fits this information is the equation for the electric field. So if we take a look at the equation for the electric field of a single point charge, it looks very similar to Coulomb's law, but remember it only depends on one charge. So the equation only has one charge in it. So for 10, we have that the electric field is K, capital Q let's call it, over R squared. So in this one, we just want to know what Q is, so we're just going to solve for Q, and that one's just as simple as plugging in. So we have that if we solve for Q, Q is, we're going to multiply by R squared, and that's going to be E times R squared, and then we're going to divide off by K. Okay. So we know the value of the electric field. It's 100 newtons per coulomb. The distance is 10 millimeters, so make sure it's in standard units, so we need to put it over to meters. Anytime you have a unit prefix, my best advice to use to not go through the whole, set up a conversion bracket and do all that. It turns out you probably will make more mistakes doing that. Whenever you see a unit prefix, such as milli for millimeters, change the unit prefix to the power of 10 that it belongs with. So for instance, milli is 10 to the minus 3. So all you do is write the number out front, so 10 millimeters, but you now just do times 10 to the minus 3 meters. That's the value for a millimeter. So it's very easy to just drop it into the unit prefix. Almost forgot to square it. Don't forget to do that, because even I do that. Divided by the value of K, which is 8.99, times 10 to the 9th Newton meters squared per coulomb squared. Okay. So calculate this, and let's just get Q. So Q is, so we have Coulomb's constant on the bottom, and we have 100 and that value, but we need to not forget to square it. So 10 times 10 to the minus 3 squared. So we get a value of 1.11 times 10 to the minus 12th coulombs. Okay. So that's our charge amount. And this equation is not going to tell you if it's a positive or negative charge. It will just tell you what the magnitude of that charge is. Simply because when we use this equation, just like Coulomb's law, we're going to usually take the absolute value of it. So whatever value you get here is not going to tell you what kind of charge it is, just how much charge you have. Okay, let me know if you have any questions. We'll take a look at 11. So 11, we want to calculate the magnitude of the electric force acting on an electron, which is placed in a 500 Newton per coulomb electric field shown below. Draw the direction of the force which acts on the electron. So we're going to find its magnitude and its direction. Okay. So we have what's called a uniform electric field. So if you haven't used that word a lot already, when you use it in the context of anything that has a direction, so for instance, an electric field has a direction. When we say that the electric field is uniform, it means that it has the same direction everywhere and the same magnitude or strength. So if I draw these electric field lines for 11, so we have these electric field lines that go downwards, meaning that the electric field points downwards everywhere. no matter what point I pick in this picture, the electric field value will be the same and the direction will be the same. That's what it means to be uniform. So we have this electron. It is given in the problem that it is an electron in this case. Call it Q. So Q is equal to negative 1.6 times 10 to the minus 19th coulombs because it's an electron, so that's given. So first of all, let's take care of it conceptually. So the direction of the force, okay? So you can either do it one of two ways. You could either memorize this, so you could say, oh, the electron will feel a force in the opposite direction of the electric field, but it doesn't quite explain why it does. So what I like to do is I like to often imagine it as, okay, if I know what my electric field looks like, I should know the charges that were responsible for that electric field. Meaning, if you see these electric field lines going down, what it means is that it would have to come from some charge. And we know that electric fields have to come from or going away from positive charges. So if I put a big fluffy cloud of a bunch of positive charges up here, it should kind of make sense that the electric field goes down and away from that cloud of positive charge. Equally, I could also say that these electric field lines will be going towards somewhere, which you could imagine that there's a big fluffy cloud of negative charge on the other end of this. And we can say, oh, the electric field goes towards it. That makes sense too. So if you can kind of picture this being true, then it should kind of make sense that this negative charge or electron would prefer to go towards the positive charges and away from the negative charges, because like charges repel from each other, and positive and negative like charges, or I'm sorry, unlike charges, they attract each other, so it'll pull the electron up. So regardless of how you want to think of it, the force on this electron would be upwards in this diagram. Either way, however we want to think of it. So also, the way I just showed you right here, visualizing it, this is a very good technique in general when you're talking about analyzing electric fields. So when we do like potential and potential energy, all that stuff that people get confused about, it's often good to visualize this because it does help every time you see an electric field to visualize it. So, but regardless, so that gives us the direction of the force. And very simply, if I want to get the magnitude of the force, now we talked about using Coulomb's law to calculate the magnitude of the electric force before, but that's when you have 2-point charges. I say I have two charges, you know, Q1 and Q2, and the force that acts to pull them together or push them apart is given by Coulomb's law. But the thing is here is that I have a charge. All I know is that it's in an electric field. Anytime you put a charge in an electric field, it feels a force. Doesn't really matter what the rest of the context is. If you put a charge in an electric field, it feels a force. And that equation is very simply given by F equals QE. That's it, okay? So anytime you know that electric field and you know the charge, you can get the force immediately. Or vice versa if you were to be asked for the electric field. So in this case, I would just say, oh, let's say if I want to get the magnitude of the force, so I just use absolute value of everything. So I do 1.6, 10 to the minus 19th coulombs times the electric field, which is given in the problem, is given as 500 newtons per coulomb. Okay. So the force, you can just easily calculate that. 1.6, 10 to the minus 19th, and 500. So we get that the force is 8 times 10 to the minus 17th newtons. Okay. Hopefully by now you should have a reasonable expectation for the values that you calculate, because for instance, you might realize that this force is extremely small, because when we used to talk about forces in the previous physics classes, we would say, oh, you know, there's 100 newtons of force. Well, this is nothing compared to 100 newtons. It's minuscule. but you have to remember that these charges are minuscule. So if you just even poke the electron, it will go flying off very, very fast because it has such a very, very small mass. So when you get small numbers, it makes sense in electricity. So let me know if you have any questions on this, and we'll move on to the next one. Okay, looks like we're good. Okay, so 12 is conceptual. So what is a measure of the amount of electric potential energy per amount of charge? So for that, if you just write it out, it will become a little bit more clear. So for 12, if you were to write the amount of electric potential energy, which we often use the letter U for, or delta U. So electric potential energy per, or in other words, divided by the amount of charge, which we often write Q. That, by definition, is the change in potential or the voltage, delta V. So the answer to this is that you can either write one of the following phrases. So you can either write potential difference, or you can write voltage. Okay. Both of these terms are used interchangeably. They are the same thing. Everywhere you mention potential difference, it's the same thing as saying voltage. So either or works here. Okay, let's take a look at the next one. What is the difference between voltage and electromotive force? Okay, they are the same thing, actually. So actually, let me add that into the list. That's a good question. I think I was going to mention that at some point when I got to the circuits, because we don't talk about it until we get to the circuits. But this also includes electromotive force, in other words, EMF, okay, for short. Now, of course, because it says force in it, it doesn't sound like it would be the same thing, because this is obviously not force. But based on the way it was named back in the day, this is what it is. So electromotive force, or EMF, is voltage, is potential difference. So it's a little misleading, but think of it as if you put a voltage somewhere. So if you supply a voltage between two places, it will cause charges to want to move between two places, so it then exerts a force on it. But think of it as the voltage causes an actual force to happen. So that's kind of, I guess, how you get the name electromotive force, but it is misleading, but it is the same thing. Let's see here. Hopefully that clears it up a little bit. For 13, a thunderstorm moves over the city of Los Angeles, and lightning is about to strike. So a uniform assumed electric field with a strength of 10 to the 6th volts per meter, don't let the units throw you off, we'll take a look at it in a second, is present between the cloud and the ground. Okay. A distance of 4 kilometers separates the charge in the cloud and the ground. So the distance between here, where the negative charge is labeled and where the positive charge is labeled, that distance is 4 kilometers. Calculate the electric potential difference between these regions of charge. Notice how it doesn't say potential energy, it's saying electric potential. Make sure you know the difference between electric potential or electric potential difference and potential energy, because even though they are very similar to each other, they're very closely related, they're not exactly the same thing. So we might discuss that a little bit more if we need to. but we're going to calculate the potential difference. In other words, we're going to calculate delta V for this. So let's write down a few things. So we have that. So we have this region of a bunch of negative charges in the cloud. And we have a region of a bunch of positive charges on the ground. I designed this problem a little while ago, and I do these kinds of problems because I'm a weather enthusiast, so I like to make up problems that pertain to the weather. So this is kind of sort of how the weather works. So there you go. The distance between here and here, let's call this distance d. We have a distance of 4 kilometers. And we know kilo is 10 to the third, so we know this is the same as writing 4 times 10 to the third meters. Okay, so we'll use that distance at some point. So we know also the electric field given in the problem. Conceptually, before anything else, so this is another good conceptual point, you should be able to draw the electric field on your own in this diagram, because we know that electric fields go away from these positive charges and it should go towards these negative charges. So the electric field should go generally upwards in this diagram. Okay. So without giving you the direction of the electric field, you should still be able to determine that on your own. Now, the electric field in this problem is given as 10 to the 6th volts per meter. Okay. Now, this is the same thing as writing 10 to the 6th newtons per coulomb. Okay. These unit combinations are equivalent to each other. The reason for that is that in here, this unit combination with the volts comes from an equation that you have, which says delta V equals minus E times D. That potential difference or voltage is based on an electric field and a distance between 2 points. If you actually just move it around to say the electric field equals the voltage over the distance, that's where the units come from. The units would be volts over meters. So that's where you get that. This one is the one that you're more used to because you use it in the electric field equation that you originally had, which is kq over r squared. You would get this one out of that other equation. So in the end, they end up being the same unit combination. So just a little side note there. Now in this one, in this problem, we want to calculate the potential difference between the two places, or in other words, the voltage. So in here, it's actually already the equation I wrote, which is delta V equals E times D. So you could just plug it into this equation. So we would have that. Now, there is a minus sign in here. Now, with these equations, you generally do want to plug in your pluses and your minuses. You do want to care about that, because with voltage, voltage doesn't have direction. It's a scalar or just a number. It doesn't. There's no voltage in this direction or voltage in that direction. As opposed to an electric field, you can say an electric field points that way or that way. If you have a quantity that is not a vector, it has no direction associated with it, you have to account for all of your signs if you want to get the actual answer. A lot of times, like especially with these delta quantities, which means change in, when you get pluses and minuses in an answer, it often indicates does something increase or does something decrease. That's the significance of your pluses and your minuses. So you cannot get the answer by neglecting them. However, you can still say, okay, let's say that the answer ends up being, 100,000 volts between this cloud and this ground here, okay? I could say that it's either positive 100,000 volts or it's negative 100,000 volts depending on the situation. But if I just want to know how big the difference is, you can always take the absolute value of it. So in general, I would say plug in your signs, but here I'm going to take the absolute value of it. simply because we don't really care so much about if something's a loss or a gain. We only want how large or what the magnitude of it is. So the absolute value of it is E, which is 10 to the 6th. We'll put it in volts per meter, so we can cancel out the meters. So we have 4 times 10 to the 3rd meters. Okay. Let's plug this in. So we have, we don't even need a calculator for this, so it's 4 times powers of 10, 10 to the 6th, and 10 to the 3rd makes 10 to the 9th. Okay, so there you go. So the potential difference, or the voltage between the cloud and the ground, is 4 times 10 to the 9th volts, or in other words, about 4 billion volts of electricity. Okay. Let me know if you have any questions on this. What I might do with this, because there are some other ideas and concepts that are very important, I might add a little bit to this problem to give you a little bit more before we move on. But let me know if there's any questions on this specifically before we carry on. Okay, looks like we're okay on questions. So what I'm going to do with this one is I'm going to add a couple of things to this question, because there's a lot of confusion between voltage or potential difference versus potential energy. So here is the thing that I will add to this question. Okay, so we have a potential difference or a voltage that we calculated. So let's consider this a little bit conceptually before we ask the question. So whenever you want to talk about potential or potential difference without talking about energy, so this is strictly potential difference or voltage. So the thing about it is that it is only associated with the source charges. In other words, whatever charges you have in your situation that are creating an electric field that's present. So here's our electric field. Whatever those source charges are, the voltage is directly associated with those. So what we can say in general, regardless of our picture, is that regions of negative charge will generally be associated with low values of V, where V is potential, and positive charges are associated with higher values of V, so high potential. Okay, you can always say this. So what happens is when you, let's say you take a proton. Okay, so we have a proton, we put it in here, and I ask you a couple of questions. So let's say that we want to answer what is the change in potential of the proton, okay, if we release it from rest. So if released from rest. Okay, we're going to assume that it goes the whole distance in the problem. We're going to compare this question to a very similar question, which is what is the change in potential or electric potential energy of the proton. Okay. These questions are very, very similar to each other. There's pretty much only one word that really distinguishes them apart, which is energy. Okay. So they're very similar concepts, but there is a difference between them. So when I ask you what's the change in potential or what's the voltage, okay, what happens is it only depends on the source charges. So for instance, if I let this proton in the middle go, I release it from rest and I let it do what it wants, this proton or positive charge does not want to be around these other positive charges. It wants to be closer to these negative charges because it's attracted toward them. So what we would see happen is that this positive charge moves upward on its own. Okay? I don't need to force that proton to do anything. It will naturally move upwards in this diagram. So if it does it on its own, we would find that it goes from high potential, or high V, to low V, low potential. So we actually will lose potential as we go up. So if I ask you, well, what's the change in potential, the value of delta V is negative, okay? Simply by going from high to low potential, that's it. So we lose potential, so we have delta V is negative. If we were gaining potential, it would be positive. Now, we already calculated that value. It's 4 times 10 to the 9th volts. But then the answer would be delta V equals negative 4 times 10 to the 9th volts, indicating that the proton loses potential as it goes from a place of high potential to a place of low potential. Okay, now that makes sense, possibly. Let me know if you have any questions on that. But versus this question, where kind of more confusion pops into play, is, well, what's its change in potential energy? Now, when you ask about its potential energy, that has to do with what does it prefer to do. So the first question only pertains to what's the source charges. We have low potential and high potential. The second question pertains more to, well, what does this charge prefer to do? So one doesn't depend on this charge in the middle, the other one does. So if we ask what is its change in potential energy, well, if it does it on its own, it will lose potential energy. And that's true in general, because if you have, like, for instance, let's say you have, like, for gravity, okay, I like to use gravity as an example because a lot of people understand it. If you have this hill and you put a ball at the top of the hill and you let it do what it wants, well, it's going to roll down the hill, okay? If it does it on its own, in other words, if the process is spontaneous, natural, occurs on its own, it loses potential energy, always. Okay? In other words, the delta U is negative to indicate that the potential energy is decreasing. So if this proton does it on its own, the value will be negative. Okay? Let's say if we do calculate it out, just to show that we get the negative with the calculation. You'll probably have to do this on the exam. Delta U equals, so you can either say it's Q delta V. This is one of the formulas that you have. But if you expand it out, it's also equal to minus Q times E times D. You can use either way to calculate this, but since we already calculated the delta V, we can just plug it in. Now, what we can do is we can plug in the charge. In this case, it's a positive charge, so it's 1.6 times 10 to the minus 19th coulombs times the change in potential, or the voltage. That was a negative in this case because we're losing potential as we lifted it up to the negative charges. So it's minus 4 times 10 to the 9th volts. This number being positive and this number being negative will give you a negative answer, which is what this is. So it indeed loses potential energy. The amount of potential energy it loses is 4 times 1.6. So it's negative 6.4 times 10 to the negative 10th joules. Okay. So that's an example of showing how you would calculate that out. If you were to use this second version of the formula that's expanded out in terms of Q, E, and D, the thing about this is that when you plug into E and when you plug into D, you must account for the directions. So for instance, for E and D, the electric field points up, and let's say that positive is upwards in a coordinate system, then you would plug in the electric field positive. If your distance D that you plug in is in regard to this charge moving upwards, it's also plugged in positive. If anything points down, you would plug it in negative, and vice versa. Let me know if there's any questions on anything related to this, and then we'll take a look at the next question. And again, feel free to let me know if there's any topics you would like to emphasize a little bit more. Because I know there are certain topics like this, which over the few years that I've helped people out with physics, a lot of people get confused about topics like voltage. So let me know. All right, so 14, conceptual question. What is a measure of the amount of charge which passes a given point per amount of time? So charge per amount of time is current. So current is the answer for 14. Make sure when you are studying and you look at your formulas, not only should you know how to use each formula and where you use them, make sure you know the basic definitions of things. If I tell you charge over time, you should recognize it as current. 15, this is a calculation in regard to it. It is estimated that when lightning strikes, you can tell I'm really a weather enthusiast, the main bolt lasts for approximately a time of 100 microseconds. When you see the tail, if you didn't notice already, the tail is micro. If it doesn't have a tail, it's an M for milli. Also, when you see lowercase m versus capital M, that is a difference in unit prefix because capital M is mega and lowercase is milli. You have a time of 100 microseconds with a current of 10,000 amps. Calculate the amount of charge that is transferred between the cloud and the ground during this time interval. What I'm going to do is I'm also going to add on another part to this question because it's something that you'll probably see, but let's calculate this for now. So let's find the amount of charge that corresponds to this current and time. So okay, so now we have that. Okay, so if you want a pretty picture, then here's the cloud and here's the ground, and you have a lightning strike happening somewhere, and we're just going to model it as just this straight current that goes between the cloud and the ground. So let me do this. So if I say that this whole area was negatively charged up here, and we have all these positive charges down here, just conceptually, if we talk about the direction of the current, well, in real life, it's the movement of electrons. So we want to remember that it's the free electrons that move around. So you could talk about which way the electrons would ultimately want to move. So for instance, you could say, oh, an electron starts out at the cloud and then it wants to go away from that and down at the ground. So the flow of electrons is downwards. So electrons flow down in this diagram. But if I ask you what's the direction of our conventional standard current, well, current is not defined with the flow of electrons. Because we often like to get rid of minus signs, we'll change something to positive. So instead of saying that negative charges move to the right, you can instead say that positive charges move to the left, and it's equivalent. So when we say the electrons flow down, it's equivalent to saying that positive charges were to flow up. Okay, so equivalent to positive flowing in opposite direction. Okay, and if you were to answer what's the direction of the current, the answer is up, because the definition of current is with the flow of positive charges, so the current flows up despite the electrons actually flowing downwards. So current is flow of positive charge. Okay, so that's a good conceptual note other than the question that we're being asked. Now, as for the question itself, we want to find how much charge passes through here given the time and the current. So we know that the current, I, is 10,000 amps, or in other words, 10 to the 4th amps. And we know that the time interval, delta t, is 100 microseconds, which is the same as 100, so you keep the number out front, and you just change the prefix to its appropriate power of 10, so times 10 to the minus 6th seconds. Okay, so that's our time interval. To get the charge, I would just say, oh, let's write the equation for current, or the definition of current. Current, I, is defined as the amount of charge that passes the point per amount of time. In this case, I'm going to solve for the charge. So the charge, we'll move the delta t over, is just the current times the time. So now we can just plug it in. So we have the current is 10 to the 4th. If you want to emphasize that the unit for current being amps, remember that an amp is a coulomb per second, and that's again just from an equation because it's in the definition that it's charge per time. So coulombs divided by seconds is the same as an amp. If we emphasize it's coulombs per second and you multiply by 100 times 10 to the minus 6th seconds, you can emphasize the seconds canceling out into coulombs. So Q equals, so that looks like 10 to the 2nd, 10 to the minus 6 is 10 to the minus 4th, 10 to the 4th, so I think that's about 10, if I'm not mistaken. So we have 10 coulombs of charge. Okay. Now, I think, was that all I had? Oh, there was one more thing that I did wanted to calculate for this. So we found the charge in coulombs, but a lot of times what we might have you do is we might have you go back and forth between the amount of coulombs of charge and the number of electrons or protons that corresponds to that amount of coulombs of charge. So for instance, I would say, okay, well, how many electrons were transferred? So then what I would say is that we know our little conversion factor is that one electron charge or one elementary charge is equal to 1.6, if you want more decimal places, O2, times 10 to the minus 19th coulombs. Okay. That gives us a conversion between the number of protons or electrons of charge and the amount of coulombs of charge. So I can use this as a conversion factor to go back and forth between coulombs and number of charges. So I would say if I took 10 coulombs of charge, I could set up a little conversion bracket. I could put the coulombs on the bottom like this. I could put in that value, 1.602 10 to the minus 19th coulombs, and that corresponds to 1 electron. Okay. So then, if I were to calculate this, okay, here's another pitfall to avoid falling into. When you use your calculator, when you have multiple numbers in the bottom that are being multiplied together in the denominator, the most common mistake that many people make is not putting that in parentheses, because what will happen is if you do 10 divided by 1.602 times 10 to the minus 19th, and you don't put parentheses, it will interpret it as just dividing by 1.6, and after all of that, multiplying the whole thing by that instead of putting it in the denominator. So make sure you don't forget to put parentheses around that, or at least just do it in a different order so it doesn't, so that mistake doesn't happen. So you use the electron charge, and then that's in the bottom, and then times 10. So we get, our answer is 6.25 times 10 to the 19th electrons transferred. Okay, so this is just a small example of showing when you're going back and forth between coulombs and number of charges. So then I could also say, here's this many charges converted to coulombs. You would use the same conversion factor and just flip your conversion factor. Okay. Let me know if there's any questions on that, and we'll move on to the next question. You mentioned that you think it's 1 coulomb. That's entirely possible, because even though I'm a grad student, I still multiplied 10 incorrectly. So 10 to the second. Oh, no, you're right. So 10 to the second, 10 to the minus 6 makes 10 to the minus 4th. 10 to the minus 4th with 10 to the 4th makes 10 to the 0, which actually 1. So you are correct, that is 1 coulomb. And that means this just goes off by a factor of 10. So this is 10 to the 18th. So luckily that was just a factor of 10, so all I had to do is just erase some zeros and fix it. That works, so yeah. Since we are talking about 1 coulomb of charge or 10 coulombs of charge, in terms of your answers when you're solving for amounts of charges, a lot of times when you get 1 coulomb of charge, it is considered a large amount of charge. For your reference, thunderstorms have upwards of 20 to 100 coulombs of charge, and that's an extreme example. So if you're getting answers that are more than 1 coulomb of charge or up to 100 coulombs of charge, make sure the situation makes sense. A lot of times your charges are less than a coulomb for many things. Let's take a look at the next example. Okay. So we have, so we got that one, 16. What is a measure of the equal and opposite charge that can be stored on plates of a blank? So capacitance is a measure of the amount of equal and opposite charge that can be stored on the plates of a capacitor per amount of voltage or potential difference. So this is literally just writing out the formula. So capacitance equals charge per amount of or divided by potential difference or voltage or whatever equivalent phrase you would like to use. You don't want to say potential energy though, because that's not voltage. And that would be on a capacitor. So now we're getting to the part where we're talking about series and parallel arrangements of circuits. So I will emphasize this. So what I'm going to do is, before I actually attack problem 17 and 19 in particular that deal with these arrangements, what I'm going to do is I'm going to give you at least 4 different examples of series and parallel arrangements, and I'm going to help you distinguish between what's series and parallel, truly. So I'm going to draw out the circuits first, and what I'm going to have you do is I'll give you about a minute to look at them, and I'll give you just a little bit of time to think about it for yourself, process those thoughts, and then solidify some answers, or if you're iffy or whatever, give you a minute to do that, and then we'll go over it, so then it will help you to realize what makes it series and parallel. So the 4 circuits that I will give you, okay, so let's say for one, I give you this one right here. A couple of these will actually just be identical to the ones in the practice test. Okay, 2. I'll use resistors for these, but it doesn't matter if they're resistors or capacitors. So if something is arranged in series or in parallel has nothing to do with what they are, if they're resistors or capacitors. They could be any circuit elements, and the arrangement is, independent of that. So 3. Oh, this one, I'd like doing this one. So let's do that. And 4. Let's do... Okay, so here's 4 different configurations of, let's just say with resistors. You could be capacitors as well, doesn't matter. I'm going to give you a minute or so to take a look at these 4. Come up with, if you think they're series or parallel, just throw your best guess out. It doesn't really matter. No one's going to judge you. No one's around to watch you anyway. You're probably sitting in your bed. But come up with a little answer, and then we'll discuss it in about 60 seconds. And then we'll see what's really in series and what's in parallel. You think you missed the... Okay, so you missed the question. The question is with these 4 diagrams that I'm giving you. Okay, so these are not necessarily on the practice test. This is just extra stuff I'm giving you. What I want you to do is quickly come up with if you think if they're arranged in series or if they're arranged in parallel for each of the 4. And I'll give you about another 30 seconds to just take a look and just make a quick guess for each of them. And then what I'll do is I'll talk about why it's either series or parallel. You'll find that a couple seem like they're obvious, but I don't think the word obvious is a good word to use here because some of them will seem obvious, but it's not quite the answer. So let's take a look at these. So now, I'll write down first the most commonly guessed answers. So what I'm writing right now is not necessarily right or wrong. So the most common answers, okay, let's use blue. Most common answers, okay. What most people say is that for these, I mean, it's pretty split. A lot of people do tend to write parallel here. A lot of people tend to write series here. A lot of people say series here, and a lot of people say parallel here. Okay. Okay. Chances are I probably guessed what a lot of you have guessed in your minds. But these will be the most common answers. So the ones that are right and the ones that are wrong. So this one is not correct. This one is not correct. That one is not correct. Okay. So the only one that is correct is this one, out of the stuff that I've written. So what makes something in series and what makes it in parallel is not based off of how it looks. Okay. Looks are deceiving. So what you need to remember is it needs to boil down to if there is a choice for charges to go one way or the other. And that choice is given by a special point called a junction. So what you always want to imagine is that, let's say that you start from the battery. So here's our battery symbol. One side is drawn longer than the other side. Okay. When you draw the symbol, the longer side is often denoted with a plus, and the shorter side is denoted with a minus. Okay. In some books and in some places, you'll also find that the battery symbol can be interchanged between this and also they write it out like this. Okay. These mean the same thing. So plus on top, minus on the bottom for the longest and the shortest side. Nonetheless, though, you want to imagine that you are, let's say you're a charge in the circuit and you run through the circuit. So what happens is if you start from the battery's plus side, and let's say you run it all the way around until you get to the minus, if there is a choice of where to go, then the things that, the two branches that define the two or more choices that you have are in parallel. If there's no choice, then it's in series. So here, you don't have any choices of where to go. You have to go through this circuit element and the next circuit element to get back to the battery. No choices means it's in series. Okay, so the answer here is series. Okay, so no choices. Here, okay, so what we're going to do is we're going to again start from the battery. So that's starting from the plus side, let's say. You go up, and this point right here is called a junction. It means that there's a choice. You could go to the left in this diagram, or you could go to the right in this diagram. So because of that, if you were to go left and you go through this branch here, and you go to the right and you go through this branch here, whatever choice you make, it is said that these two branches that define those two choices are in parallel to each other. Okay? It's because there's a choice of where to go. Okay? Not because it looks like it's in parallel, but because there's a choice. So it doesn't matter how it looks. In fact, what I'll show you here is that if you don't like the diagram the way it looks, redraw a different way. So what I would do with this diagram personally is, again, you start from the plus end of the battery. So I'm going to draw a diagram on the side. So here's my plus end of the battery. I'm just going to indicate with a point. All I'm going to do is I'm going to go left to right in my picture that I'm going to draw, and I'm only going to identify the most important features. So for instance, if I approach this point here, the first most important thing is the junction. So all I do is I show that I split into two separate paths. Okay, so there's a fork in the road. Along the left path, I would draw one resistor in this case. So let's just say the top branch is the left path. On the right path is only one resistor, so we only draw that resistor. Eventually, the two paths will approach another junction, but instead of splitting, they combine together. So they then combine together, and they go back to the battery, so it goes out. When you draw the diagram like this, it's much more obvious that it's in parallel to each other, because you can see the split, and it's intended to be drawn parallel. But just note that when you have diagrams like this, it doesn't have to be drawn parallel. It might be useful if you do this, if you want to. Now, the rest of these, this one's parallel, and the reason for that is, again, because there's a junction, battery, two junction, split. Okay, there's a choice between the two resistors before they go back and they join and go back to the battery. So, parallel. Okay. Here, this one's definitely parallel. Not only does it look parallel, but it is parallel because there's a split. That's the most important thing. So there's a junction that determines the choice that you have between the two branches. Okay. So I hope that clarified any possible uncertainties or doubts you had about what's in series and what's in parallel. So identify it by the junctions or the splits, whether if they're there or if they're not. Okay. I see that there's questions. Okay, you made a guess. Cool. If you had an odd number of resistors, would that affect the outcome? If you had an odd number of resistors, well, the number of resistors doesn't necessarily have anything to do with if they're in series or parallel. So let me draw very quickly another example with more than two resistors. You could replace them again with capacitors and it doesn't really matter. So if you had, for instance, let's say this circuit, okay? Okay. So this is kind of like the one that I just drew up here. Now, with this one, okay, so we have 4 resistors. How does that affect if something's in series or in parallel? So I say not necessarily. It's kind of it's a question where it's like it's very situational because it depends what exactly I'm asking of you. So let's just say that if we have this resistor R1, resistor R2, resistor R3, and R4. Okay, so we have these clearly labeled so we know what's what. Now, I could ask you, is this resistor in series or parallel with this other particular resistor? And I could do that for any of these resistors. So when you have more than 2 resistors, it really just depends what you're asking with respect to what other thing. So for instance, if I asked you, is R1 in series or in parallel with R2? Well, then it's in series, because when you take R1 and you go from R1 to R2, there is no choice between R1 and R2. You have to go through both R1 and R2. There's no options there. So we could say that from here, R1 and R2 are in series. Okay, that's a true statement. Equally, you could do that for 3 and 4. So 3 and 4 are also in series because there is no choice of where to go between R3 and R4. There's no split-offs between them. So you have to, if you go through R3, you have to go through R4. So we can also say R3 and R4 are in series. Okay. But then you could also ask, well, how about these 2 resistors, R3, and these 2 resistors, R1 and R2? What are they in with respect to each other? Well, that's parallel, because I could say, oh, let's go to the right. That goes through 1 and 2, but not 3 and 4. And I could go to the left, and that's going through R3 and 4, but it's not going through 1 and 2. So we would say that R1, let's call it R12. Okay, so in my notation, when you write on the subscript, whatever numbers you write is the equivalent resistance between those resistors. So what this means is the equivalent resistance of 1 and 2 together, that resistor is in parallel to resistor 3, 4. In other words, the combination of 3 and 4. Okay? So you can see here that, okay, well, I have more resistors, and the answer is that it depends on what you're asking with respect to what other thing. Okay. Now, when you solve a circuit, like you will probably do on your test, not a very complicated circuit, but maybe something like this, when you solve it, again, I don't generally like diagrams like this. What the first thing I do is I redraw the diagram in a way that's more helpful to me. So what I do is I take this diagram and I say, oh, I start from the battery, I go to the junction, I split. Let's say the left path is going along the top, so we go through R3 and 4 in one of our branches. So R3 and R4. And if we do the other one, that's 1 and 2 in the other branch. R1, R2. Those 2 paths combine back together to the other junction. So they combine and they go back to the battery. Okay. When you draw it like this, it's a lot easier to interpret, because what you would then say is, if you start in the branch, these 2 are in series, these 2 are in series, so series, series, and then if you were to treat the combination, so if the boxes that I drew, if you treat them as one single resistor now, so you take the 2 out and you replace it with a bigger one. If you were to have these 2 resistors, you would then say that these 2 resistors are in parallel to each other because of the 2 branches that they're in. So parallel. So you can kind of see the additional layer of complexity that you get when there's more than just a couple of resistors in place. So combine stuff in series and then combine them in parallel. So it's kind of almost like layered like an onion, if you will. So hopefully that answers your question. To follow up, you asked that, could you say that R1 is in parallel with R3? Yes, you could, but, and I say this with a huge, drawback. So you do not want to combine R1 and R3 if they're in parallel. The reason being is that if you look at the diagram, this is why this diagram really helps a lot to interpret what happens here. Despite R1 and R3 being in parallel with each other, that is a correct statement. Despite that fact, you cannot combine them in parallel. In other words, you cannot do 1 over R1 plus 1 over R3 and then expect to get an answer for that. That's correct. The reason being is because if you were to combine R1 and R3 in parallel into an equivalent resistance that you would say that you calculate it for a problem, the problem with that is that in this diagram, which we say is the same as this diagram but easier to follow, if you combine R1 and R3 in parallel and you put that one resistor somewhere, the problem is no matter where you put it, like if I put that resistor here next to R4, well, the problem is R1 was never in series with R4. And if you put the combination of R1 and 3 next to R2, well, then the problem is that R3 was never in series with R2. So you would never combine it in parallel. What you would do is you would start in the branch, combine the things in series in the branch first until you get it to one resistor. Do that for any other branches you have, so you combine in series within the same branch until there's one resistor or capacitor per branch. Then, once you only have one per branch, then you combine them in parallel. So, despite R1 and R3 being in parallel, you would never combine it in parallel. Perfect. And a question I got before, if the battery for number 2 was placed, I think I erased it earlier. I think it was 2 the same as the one that I drew above? I think it was. If the battery for number 2 was placed on the leftmost branch, would that make a difference? Yes, it would. Regardless of whatever circuit diagram you're referring to, 1, 2, 3, or 4, regardless, if you move the circuit element into a different branch, it's going to behave differently most of the time. So in any of my drawings, if you move the battery to a different branch or a resistor to a different branch, it would change the configuration of series and parallel for each thing with respect to each other. Awesome. Any questions before we actually do problems number 17 through 19, given our knowledge of series and parallel? Looks like we're relatively good, so I'm going to start on 17 now. Feel free to continue dropping any questions. So let's take a look at 17. For the capacitor circuit, so we're going to do a capacitor circuit first. If C1, so in other words this capacitor on top, has twice the capacitance of C2, the capacitance on the bottom, how much charge will C1 have on it compared to C2? So we know that C1 has twice the capacitance of C2. And what we want to know is how much charge it will have on it compared to C2. So there's a couple ways you can look at this, but I'm going to refer to the technique that I kind of showed you earlier of when you're comparing one thing to another. It was that little thing that I called a proportionality. It's a very useful technique here to use. So since I have capacitors, I know that there's an equation for capacitance, and there should be one equation that immediately on the spot pops to your mind when you see capacitors, and that's the definition of capacitance. This equation is used very extensively when we talk about the stuff on the capacitor, like the charges, the voltages, etc. So for capacitance, so this is 17, capacitance, by definition, is charge divided by the potential difference or the voltage across it. So what I was saying about using proportionalities to solve this problem. Okay, so if I want to actually in this one, we won't need it because our conceptual knowledge of how things are arranged in series and parallel actually gets the answer immediately before that. What I would have done is I would have attempted to solve for the charge and then put it in terms of the capacitance and the voltage across it. What I would have done is said that, oh, if you change this by this amount, then it would change this by this amount. We don't need that here. What I'll do is I'll show you in a moment how you might use this in a similar example. But in this example, you just realize the fact that the two capacitors are in series with each other. So if you have that, here's your battery, your capacitor C1 up top, and your capacitor C2 on bottom, so C1 and C2. Okay. And we know C1 has 2C, and we know that C2 has C. So in other words, whatever the value of C is, we just say that this one has twice the amount of that value of C. So if we could redraw this if we wanted to. It's not that difficult, but if we did redraw it, we would start from the battery, we would follow this, we would hit a first capacitor, C1, no splits, no junctions or anything. We get to C2, so we just continue straight, get back to the battery, and that's it. Okay. So in here, when you rewrite this, it becomes much more clear that it's definitely in series. Okay. But when you have capacitors in series, okay, I want you to remember two very important ideas. Okay. So the first thing is that. So one, I want you to remember that the charge on each capacitor in series is the same. Okay. In other words, if there was a Q1 and there was a Q2, the value of Q1 is equal to the value of Q2. And furthermore, if I were to find the equivalent capacitor or the equivalent capacitance of the two, I merge the two capacitors together and essentially treat it as one single capacitor. Call that capacitor C12. If I had such an equivalent capacitor that just behaves as one capacitor, that equivalent capacitor would also share the same charge. So the charge on that equivalent capacitor would have the same charge as any individual one, given that it's in series. So that's one. And the other thing you want to remember for series, so two, is that the voltages across each capacitor add to a total. Okay. So if they're in series, if we have a voltage across one, so the potential difference between 2 points on either side of the plate is the voltage across it. If we have the voltage across one and we have the voltage across two, whatever those two voltages are, they add to each other to a total. So in other words, let's just say, so if what this says is delta V1 plus delta V2 equals the total, which is the voltage across the equivalent capacitor, call it 1, 2. So the voltage across this plus the voltage across this equals the voltage across the entire thing. If that's the case, what I would then say is let's say hypothetically that this was a 12-volt battery. Okay, so we connect a 12-volt battery into the circuit, and we want to find the voltages of each of them. What might be a possibility is, let's say, for example, i.e., if battery is 12 volts, so epsilon equals 12 volts. A lot of people say E, but it's technically epsilon. it's 12 volts. Perhaps. Okay, so what could work is delta V1 equals 8 volts and delta V2 equals 4 volts. I could have 8 volts across this first capacitor and I could have 4 volts across the second capacitor, and they add up to 12. That's it. Okay? They don't have to be the same value. They can be. It could be 6 and 6, but it could also be 8 and 4 or 5 and 7. The exact values of those voltages are determined by the values of the capacitances. So if one capacitor is twice the capacitance of the other, it could have an effect on what those voltages are. But at the end of the day, they would have to add up to 12 if the voltage across the whole thing, or the battery voltage, is 12. So that's just a little example of that. So remember that for series. Okay? I will quickly write out what it is in parallel, which is actually just the other way around. If you were to have, for the parallel, so good conceptual knowledge. So if you have this sort of thing happening, okay, anything that's equivalent to putting them in parallel, regardless of how the diagram looks, your two important things will be, one, charges on each capacitor add to a total. Okay. The reason being is that charges have to flow through the circuit, and because of the junction, which is what defines it to be in parallel to each other, there's choices of where the charges go. So whatever charges come into this, some of them split off to one of the capacitor, and some of them split off to the other capacitor. So therefore, when you add the two charges, they add back into the total that you originally had. So in other words, Q1 plus Q2 equals the charge on the equivalent of both of them together. And then the other statement is that the voltages are the same. Okay, so the voltages are the same. So the delta V1 equals the delta V2 is the same as the delta V for the entire thing. Okay. Make sure you know these very well conceptually, because they'll take you a very, very long way. So to use this to answer the question, I wanted to know how much charge C1 had compared to C2 in our diagram, but since they're in series, the charges are the same on both of them. So despite them having twice the capacitance, they have the same charge. So in here, what I will say is that Q1 equals Q2. So in our example, for number 17, Q1 equals Q2. Okay, so it has nothing to do with the values of the capacitances. But if I were to reword the question for you, I could ask you, well, how much voltage does one have compared to the other? So this is where I will use the equation to show you that one will have twice the voltage as the other. So for instance, if I wrote, so what about voltage? Okay, what this would mean is that if we know that C equals Q over delta V, which is the relevant equation for capacitors, and I solve it for the voltage, because that's what I want here, so charge divided by capacitance, okay, what I'm going to do is I'm going to use that idea of proportionalities from earlier. So to recall what I did earlier, a proportionality means to ignore things that do not change from one to the other. So in my situation, I am comparing two capacitors to each other. One has twice the capacitance of the other. So when I compare the two capacitors to each other, what things stay constant? So when I write delta V is proportional to, we write that symbol, we get rid of things that stay constant. In other words, the charge stays the same on each capacitor, so we ignore it. So we replace it with a 1. The only thing that does change is the value of the capacitance. So at this point, if you were to ask what happens to the voltage if you double the capacitance, then we have it's 1 over twice the amount of capacitance, which means that the fraction is a half. So when we have twice the capacitance, it ends up being that we have half the voltage. So then we would say that, let's say if one has twice the voltage of the other, it would mean that one would have like 4 volts and the other one would have 8 volts. That's how you would achieve that. So anyway, this is a lot to take in. So let me know if you have any questions on anything that I talked about with these capacitors in series and in parallel. Let's see. All right. Okay. So it looks like we're fine on questions. So what I'm going to do is I'm going to flip through the other couple questions here. So let's quickly just toss number 18 out of the way. So blank is a measure of how much the flow of electrons through a path is hindered. Anytime you're talking about hindering the movement of charge, specifically, let's say here electrons, when you're trying to stop it or you have things getting in the way, that's called resistance. So resistance is a measure of how much the flow of electrons through a path is hindered or slowed down. The units for this quantity are in ohms, OHMS. So now the other one, 19. So this is the other one I wanted to get to. So this will kind of tie all the loose ends together, okay? As far as series versus parallel. So on 19, we have what percentage of the total current, in other words, leaving the battery. So you have your battery in here with some voltage. You have the current leaving the battery going up to the top part of the circuit where the junction is, and it's going to split. We know that's going to happen, so we know this is in parallel. So we want to know what percentage of that total current before it splits will R1 receive if it has twice the resistance as R2. So R1 has twice the resistance of R2. So the analogy is that, you know, you have the flow of traffic and, you know, let's say you have a choice between taking the 405 and the 118 freeways. The flow of traffic kind of behaves similar to how we have the flow of electrons in a way. It's good to a very good extent for the analogy, where if you have two paths that you can possibly take, so in this case we're going to draw two resistors in each of the paths. Okay. So the circuit diagram that I'm drawing here, if you were to just imagine a battery connecting the two ends, this circuit diagram is exactly the same as the one in the problem. So for this parallel arrangement of resistors, so we have two paths that we could take. If one path, you know, let's call it R1, has twice the resistance as the other, so R2 has some resistance R, whatever that value is, and R1 has twice that same value. So it could be 50 and 100, it could be 100 and 200, and etc. Given that we know that, we want to know what happens to the current. So if current is just the flow of charges past a certain point, we're just asking which branch gets more flow compared to the other. Now, the default answer you would give out is, okay, well, there's two choices. We'll just flip a coin, right? Charge could go to the left or could go to the right. So you might be inclined to say, oh, it's 50-50. But the thing is if you were driving and you had a choice between two different freeways and they would both get you to your destination, let's say that it's very simple, you know, same distance, same everything other than which one has more traffic, okay? If you had a choice between two freeways, I would imagine that you probably would not choose the freeway that's more congested. So you're much more likely to go in the path that's more open and free with less resistance. So the charges will take the path of least resistance more than the path of more resistance. So if this branch with R2 has less resistance than the branch with R1, we can imagine that more of the charges will be flowing through this branch. So there's going to be more current going through the smaller resistance. With that, you could already tell the answer is not 50-50, and you could tell that this branch has to receive more than 50%, while this one has to receive less than 50%. So here's what we're going to do. If you use the equation for Ohm's law, because this is how you relate the current to the resistance and voltage. So we want to know something about the current. So we take Ohm's law, V equals IR, or R times I, or however you write it. We want to know about the current, so we solve for the current. Okay. Voltage divided by resistance. We're going to exploit the proportionality again. So I'm going to say that when things are in parallel, the voltages are the same. So notice that when we did the capacitors, the voltages were the same in parallel. That's true regardless of the circuit element. The voltage will be the same in parallel if something's in parallel. So if the voltage across each of these is the same, we can just ignore the voltage pretty much. So we can say that the current is proportional to 1 over the resistance. So when you use this here, what would happen is if you plug in the factor by which you're changing the resistance by. So in other words, in this diagram here, if you put twice as much resistance, then you would say, let's just drop a 2 into here. What would happen to the current? Well, the current would cut in half. That's it. Twice the resistance means half the current. So the current in this branch is half the amount of current compared to this other branch. So how does that allow us to then determine the percentage? Well, then this is how we do it. If I were to say that there was a current in the smaller, actually, sorry, not that one. Let's do the top one. If there's a current that goes through this top branch, let's call that current just a value of 1. Okay, 1's a very easy number to work with, so we're going to call the smallest current a value of 1 to make our lives easy. What that means is that if I had a current in the bottom branch, we know according to this that it would have twice as much current as the one with more resistance. So this one has a value of 2 compared to that one. But since you know the currents have to combine together and come out, they have to add to a total, so the total will be by default 3. What you can then say is, well, this makes up 1 out of 3, and this makes up 2 out of 3. So in the top branch, it's 1 out of 3, which is 33%. And you can say in the bottom branch, that's 2 out of 3, which is 67%. So the answer to this question is 33%. Resistor 1, because it has twice as much resistance, gets half the current, which is actually 33% of the entire current in the circuit. Let me know if you have any questions on how that works. Okay, looks like we're good so far. Everybody seems good. All right. Most of you are still here, dedicated. Awesome. So in this practice exam, if we take a look at this. Okay, so on this one that I made back in the summer, I only put that and this question pertaining to circuits, and that was the extent of it. What I'm going to do is after number 20, I'm going to also add in another conceptual question about RC circuits, because I know that's another topic that we cover that's maybe a little bit confusing. So I'll talk a little bit about RC circuits after number 20 if you want to take a look at that as well. And then we'll kind of end on some of the magnetism stuff. And then I'll take any other questions that you have generally. So for 20, We have a 3 amp current that flows from left to right in this diagram, so from point P1 towards point P2. It goes through resistors R1, which is given, and R2, which is also given, so 100 ohms and 200 ohms. We have the circuit diagram. We're going to calculate the total voltage across both the resistors. So all the way across the whole thing, what's the voltage from P1 to P2? So remember that when you're doing voltages, which is equivalent to saying potential difference, which is a term which kind of helps you to realize what you're doing, potential difference is the difference in potential between 2 points of your choice. So if I ask you what's the potential difference between P1 and P2, I'm asking you to find the voltage between P1 and P2 across both of these resistors. It's the same thing. But saying potential difference kind of makes it a little bit more obvious that there are 2 points of interest involved. So, for example, if I told you P1 had a potential of 12 volts, and I told you that P2 had a potential of 36 volts, well, the potential difference between 12 and 36 is 24, and that's the voltage across both of them. That's just a hypothetical example. But just to clarify what we mean by that. So in this one, we know what the current is, and we know the resistance is. So let's write that out. So again, what we're going to do is we're going to talk about some of our conceptual knowledge of how things are arranged, whether if they're in series or if they're in parallel. So the one quick thing I'm going to write about resistors, kind of how I did with the capacitors, I'm going to write a couple of statements for series and a couple of statements for parallel for you to have to reference to when you're solving these circuits. So when you're doing this in series, which is what we're doing in this case, okay, series, we have one, current is the same through the entire branch. Okay. If you're talking about a branch of the circuit, everything in that branch is said to be in series. So the current is uninterrupted. It does not split between 2 different locations. It continues through the entire branch. If it's in series, it's the same current. So I1 equals I2 is the same as the current through both of them. 2, voltages add. Okay, so delta V1 plus delta V2 equals delta V12. This is the same as the capacitors. Okay. Notice that if you replace the word current with charge, the charges are the same in series on the capacitors. It does line up with the capacitors. So, and then parallel. Okay, one current adds to a total. So if you have 2 parallel branches, the currents join together and add into a total. So I1 plus I2 equals I12, which is the total. And then 2 voltage is the same, are the same. Okay. So these are all the important points that you want to remember conceptually. Okay. Now, for our particular example, so 20, we have this series combination of 2 resistors between these 2 points. So we have R1 and R2. We know their values, 100 and 200, easy. Okay. And we know the current that goes through them. Now, because these 2 are in series, it doesn't matter if I tell you the current for 1 or the current for 2, they're the same because the current has nowhere to go. It has to go through both of them. So the current that goes into and through resistor 1 is the same as the current that goes to and through resistor 2. So I1 and I2 are the same. If we were to treat these two resistors as one single resistor, the equivalent resistance, and we call that resistor 1, 2, the current is still the same value, and we know this would be given, which is 3 amps in the problem. Okay. Now, in order to solve this, so if we want to find the potential difference across the entire system from one end to the other, the potential difference between these 2 points, or the voltage, can be found using Ohm's law, but you are doing it across the entire thing. So it is the voltage or the potential difference across 1 and 2 together. So you must, when you write Ohm's law, it states that delta V equals R times I. You must write it for the whole thing. So in other words, delta V 1, 2 equals resistance 1, 2, current 1, 2. Right? When you use Ohm's law, you can only use it on one resistor at a time. But if you can treat the resistors as if they were one resistor, you can use it on that one resistor. So what I'm saying is, if we were to treat these 2 resistors as one single resistor with a resistance R12, that one resistor we can use Ohm's law on, and we can solve for something here. So what we need to get is the resistance of them both. In this case, the equivalent resistance of 2 resistors in series is just adding their values together. So we have one equation where you just add the values, and there's another equation where it's 1 over the resistance added with other 1 over resistances. This one is just adding them up. So it's real simple. Okay. So this was in series, not in parallel. Okay. It's 1 over if it's in parallel. It's equal to 300 ohms. Okay. That's it. Because it's 100 plus 200, so we get 300. And we know the current is 3 amps. So everything's in standard units, so we just plug it in. So the voltage, or the potential difference across them both, is 300 ohms times 3 amps, which is 900 volts. That's the answer. So now, just to kind of give a little bit more depth to the problem, just to give you other possible questions that you could be asked, so you kind of get a range of what you need to know. I could also ask you about particular circuit elements. So for instance, I could ask you, what's the voltage across R1 only? So if I ask you, so what is the voltage across, or in other words, potential difference across R1. Okay, so if I ask that, if you remember that when you use Ohm's law, you have to use it on one resistor at a time, what that would then mean is you have to write delta V1 equals R1 times I1. Okay, notice how all the subscripts are consistent with each other. It all deals with the same resistor. So now, this equation is already solved for the voltage, so all I would have to know is what's R1 and what's I1. So R1 we already know, it's 100 ohms. I1 is also known because we said that the current through 1 is the same as the current through 2, which is the same as the current through the combination of them, which is 3 amps. So it's 3 amps. If that's the case, we get 300 volts. Okay. You could then conclude that if you were to do the same thing for R2, so if I ask the same question for R2, you could do the same thing and you would get 600. You know, delta V2 equals R2 times I2, and you plug it all in, you get 600 for that. Okay. If you want to try it, go ahead. You'll get 600. And what will happen is this will confirm one of the other facts that you should already know. Notice how you have 300 volts and you have 600 volts. These two resistors are in series, which means that the voltages add to a total. 300 volts plus 600 volts is 900 volts, which is what our answer was. So the two individual voltages in series add to the total. Okay. So that should make sense. You could also figure out this pretty easily because you could also realize R2 has twice the resistance as R1. If R2 has twice the resistance, according to Ohm's law, if you double the resistance, it doubles the voltage. So notice when you change it from 100 ohms to 200 ohms by doubling the resistance, you just get double the voltage. So you can also do it very easily that way as well. Let me know if there's any questions relating to any of this, and then we'll go over RC circuits real quickly. Let's see if we can aim to be done not too long after 10:30. Let's see how we can do that. Question, so both sides have the same electric potential because it's the same as voltage. Be a little bit more careful of how you word that. So when you say electric potential, okay, so when you use the word potential by itself, you don't say potential difference, you say potential. It implies that you are mentioning only one point. So I could say there's a potential at that point, and I could say that there's a potential at that point, separately, okay, so singular. When I say potential difference, I'm implying there's 2 points and you're comparing the two. So for instance, let me erase this and let me give you a hypothetical here. If I told you that I had a circuit, let me actually kind of show you something here that's going to be kind of helpful for you conceptually in terms of potentials. Let's just say that we had this circuit here. Okay. Let's just look at it conceptually. We're not going to solve it, we're just going to look at it and analyze it a little bit. So we have this resistor R1, R2, and R3. So first of all, let me refresh your memory here. So notice that when you go from the battery, you go to R1. Okay, there's no choices yet, so this is just one continuous path. There is a junction right here after R1, so it splits, okay? Splits into two paths, and they each go through their respective resistors, which means that R2 and R3 are in parallel, definitely. Joins back together, goes back to the battery. So what we say is that R2 and R3 are combined in parallel. Once you combine it in parallel, then it's in series with R1, okay? Now, besides that, voltage and potential difference. So let's just say that I told you that this was a 12-volt battery. Okay, so the battery is 12 volts. And we know that the longer side signifies the plus side and the shorter side signifies the minus end. Now, the plus and the minus, the only thing that they do mean is that one side is a higher potential and the other one's a lower potential. It's kind of like how I mentioned earlier, when you have a region of positive charge, it's a high value of V or potential, and there's a region of negative charge and it's a lower potential. So plus means high, minus means low, that's it. So what we do is when we talk about batteries, okay, the only thing that's important is that the potential difference is 12. The voltage is 12. In other words, if I had a point above the battery on the plus side and I had a point on the minus side, and I asked you what is the difference in potential, delta V, between that, that's 12. Okay? When we say it's a 12-volt battery, that's what we mean. What this could mean, though, is let's say if the bottom was 0 volts, okay? So we define that to be 0 volts. What this would then mean is that, according to this battery, if the top has to be a higher potential than the bottom, and the difference is 12, that has to mean that the top is positive 12 volts, because 12 minus 0 gives you 12. But I could, of course, make the bottom 12, and the only thing that still needs to be true is that the difference is 12. So then if the bottom is 12, the top is 24. So the difference is 12. I could tell you I have a battery with 1 million volts on the bottom side, and that sounds very scary, but it's not scary because the top is only 1,012 volts. So the difference is 12 volts. It's not dangerous. So when we talk about the potential at a point is the value it is at that specific point. Potential difference is referring to the 2 points, okay? When you progress, for instance, through this circuit, what will happen is, let's say this is a 12 volt battery and we call the minus end 0. You should always just call the minus end 0. Top is 12. If you have wires and there's nothing, getting in the way, if you just travel along the wire, the potential remains the same, ideally. So in other words, this point right here stays 12, this point here is 12, that point there, and all the way up till the resistor, it's 12, okay? On the bottom, this is all directly connected with nothing getting in the way, okay? So all of this wire on the bottom would all be 0, like this, all the way up until you hit the resistor, okay? So it would be 0 all the way up to here. The moment that you cross over a circuit element, the potential changes to a new value. So for instance, let me just make up some dummy values. You would, of course, calculate this in a problem, but let's just use some dummy values. I could say that this point right here was 8 volts on the other side of this resistor. What that would then mean is that this point here is 8, this point here is 8, this point here is 8, up until you get to that circuit element and you do not cross it. This point's 8, 8, and 8, okay? This is how the potential looks like through the entire circuit. So if I ask you to find the potential difference or the voltage between 2 points, what it means is to compare 2 of these values. So for instance, if I wanted the potential difference across R1 or the voltage across R1, that would be 12 minus 8, which is 4. That's the voltage across it. If I ask you across R2, that would be 8 minus 0, which is 8. And over here, 8 minus 0, which is 8. Okay, so that's just a little bit more depth to help you to better understand potential difference or voltage versus anything else. So one last note here is that you'll notice that the 2 resistors that were in parallel have the same voltage, like we said. We said that things in parallel have the same voltage. Well, here it is, 8 and 8. This is the reason why they have the same voltage. So anyway, let's see. Hopefully that answers your question about that. Does anyone else have any other questions? And then what I'll do is I'll quickly go over the RC circuits. Okay, so let's take a look at RC circuits real quick. Okay, I'm going to hit a couple of major points. If you would like me to talk about anything about RC circuits in particular, drop them in the comments and I'll take a look at them after I briefly go over something. So go ahead and drop anything you have related to RC circuits so I can take a look at it in a moment. Okay, so there's a couple things I want to hit on conceptually. I'm not going to go too much into equations, at least for the time being. I just want to hit some conceptual points that you'll probably encounter. Okay, so for the RC circuits, you have some battery a resistor and a capacitor hooked up together. Okay. Now, here's what the RC circuit boils down to ultimately. Okay, so you have your resistor and your capacitor. So what does it do? So charge has to get from one place to another. So you have a flow of charge, or in other words, a current. Okay, so now you have a flow of charge. Now there's a resistor in there because it modulates that flow of charge, because without a resistance, okay, you know, let's just say if you had this circuit hypothetically, if you only had a battery and a capacitor, okay, this would not be an RC circuit, but we can think of it as an RC circuit in a way, because technically in real life, wires do have a resistance, but the resistance is often very, very, very small, to the point that we neglect it because it's so small compared to any other things we put in the circuit. We usually don't talk about it. But we would say that the resistance of all the wires would be practically zero or zero. The thing is that if you were to talk about the current in the circuit using Ohm's law, and you solve it for the current, okay, this would give you what the current would be. There would be some voltage which would be supplied by the battery, let's say 12 volts. But the problem would be that if the resistance was zero, well, guess what? You're taking some number and you're dividing it by zero. When you divide by zero, well, the answer is it's undetermined. So you can't do that. Well, now the value that you would essentially approach by doing this is when you divide by a number that's practically zero, well, zero can go into any number an infinite number of times. So the answer approaches infinity. So to have an infinite current in here would mean a couple of things. Number one, it would charge your capacitor instantly. There's no delay. Number two, if this were real life and you had an infinite current going through things, let's just say that things would heat up very, very quickly and it might start a fire. So anyway, we have a resistor in here, so it slows down the flow of the current. So there's a rate at which the charges are delivered to the capacitor, and it takes time to do it. So now, in the end of this, okay, what I'm getting at is the capacitor. What you want to know is that at time zero, okay, so when you, let's say if you have a switch in here, you know, the only purpose of the switch here would be to turn it off and on. When you close the switch and turn it on and let the current start to flow, so switch closed, okay. So at the very first moment that you close the switch, there is no charge on the capacitor, okay, because it's initially uncharged and it takes time for it to charge. The current is equal to its maximum value, okay, and this is equal to, in terms of your equations, it's equal to the voltage of the battery, which is often denoted with this, divided by the resistance. So this is actually just Ohm's law. Okay. The current is at its maximum value the moment you open the switch. Okay. Notice how when you look at the graphs for these, one of them kind of increases over time and the other one decays with time. So the current will decay with time and the charge will grow with time. The analogy that you want to use for understanding how this works is to think of it as like you going to a buffet. Okay, so if you go to a buffet with an empty stomach, you are extremely willing to accept food. So the rate at which you eat the food is very fast. The current, the flow of charge into the charge storage, the capacitor, is fast. But as that capacitor gets filled with charge, as you continue to put charge onto the plates of the capacitor, it fills it up, so it's like you eating more food and then getting full and more full and more full until you don't want to eat anymore. So the current will slow down, so it's like saying that you start eating more slowly until you stop. That's basically how it behaves. So That's the basis of the RC circuit. So this is at time 0, and then we said that as time approaches infinity, so after a very long time is what we say, a very long time, okay. As we continue to let time pass on, the charge on the capacitor is at its maximum value, and it's equal to the voltage of the batteries times the capacitance. So we often write it like this. This is just your capacitance formula, you know, Q equals C times V. That's just the capacitance formula. And if you want the current approaches 0. Okay. These are some of the most important points to remember about this. There are, of course, the equations that have the exponential decay and everything, and you should know how to use those. But in terms of conceptual knowledge, these are some very important points to remember. Okay. Let me see if you have any questions on the RC circuits in particular. You have a general question. When we look at a battery with resistors, we talk about currents, and when we look at capacitors, we talk about charge. But with RC circuits, in terms of charges and currents, that is correct. When you talk about the resistors, you talk about charges moving through them as a flow, so that's a current. And when you talk about capacitors, you have two separate plates in which stores charge on them, but does not permit charge to go from one to the other ideally. So there's no current across the plates, it's just charge on it. So resistors, we talk about current, and capacitors, we talk about charge. So therefore, when we do RC circuits, it makes sense to talk about the current that goes through the resistor and is delivered as charge to the capacitor. Hope that makes sense. If anyone else has any questions on the RC circuits, let me know. There's one other little thing I need to mention to you because it's another important thing you should know about the RC circuits conceptually. You might see this on the test. So the last thing I do want to mention, other than any other questions you have, is that the time constant, okay, there's a couple of things you could talk about with the time constant. I could go on for a little while, but I'm going to try to cut to the point here. The time constant is a way of thinking of how fast the capacitor will charge. So relates to how quickly or slowly the capacitor charges. Okay. So how do we know that? Well, we have this equation that describes the charge as a function of time. Q equals Q max 1 minus e to the minus t over RC. Okay. But what I'm going to do is I'm going to write this RC as the Greek letter tau, which is our time constant. So tau. Okay. So a couple of things. In this equation, which is what you'll be given on your formula sheet, Q max will be probably written as what I have written here, which is C times epsilon, which is the voltage of the battery. So when you see this out here, that is your Q max. Over here, you might see it written as RC in the place of the time constant in the denominator of the exponent. But if it's written as RC, that is the time constant. So tau equals R times C. Okay. So if you know the resistance of the circuit and you know the capacitance of the circuit, you can figure out the time constant. Now, where I was trying to get at was relating to how fast it charges. So the thing is that if you plug in different values for the time constant in this exponential function, it actually either makes the function more or less steep, so it decays faster or slower, or grows faster or slower. So what we can say is that, let's say if I draw out the graph for you so you can kind of visualize this. Okay. So on the graph, let's say if I plot the charge on the capacitor versus time, which is what this function describes, the shape of the graph will be the following. So if there is a maximum charge that can be stored on the capacitor, so therefore there's an asymptote right here that it cannot pass, charge will, there's a lot of charge being put on the capacitor at the beginning, and the rate at which it is put on it is going to slow down over time. So it eventually just caves out and you don't get too much charge on it later. So there's going to be some unique value here for t equal to one time constant. Okay, so the time constant is measured in seconds. So when you put in a resistance and a capacitance in standard units, you'll get a time constant in seconds. There is a way that the units do work out to show that's in seconds. But anyway, there is a unique time that corresponds to that time constant, and it corresponds to a specific percentage of completion on this curve. Okay, that percentage of completion, depending if you're talking about the decay or the growth, is either 37 or 63%. Nonetheless, notice how if you were to change the value of the time constant to a bigger or smaller value of time, it would correspond to if you go higher or lower on this charge curve. So if the value of the time constant is larger, then, so what would happen is, let's say that you were to move this time constant value to a larger value. So the value of tau is now bigger, okay? So you move it over to here. What that would mean is that it would take less time for the capacitor to charge up to, actually is that, hold on, let me make sure that's correct. I want to say something that's wrong here. If you slide out the, if you slide the time constant out further, no, it's the other way around, okay? If you slide it out further, what happens is this curve stretches out, and what happens is this will do something like this. So if we had a time constant being over here, it would stretch the curve out more so that you would achieve the same percentage after that time, okay? So having a bigger time constant actually means that it takes more time to achieve the same amount of charge, which means it charges more slowly. So if tau is larger, then capacitor charges more slowly. Takes more time to charge it. Okay, so if you had to compare which circuit charges faster, you can rank them based on their time constants. The largest value of the time constant means it charges the slowest. Let me know if you have any questions, and we'll finish up the practice test. Looks like we're relatively good. Okay, so what I'm going to do is I'm going to quickly do a little bit of the magnetism. Again, drop anything you have down into the chat to let me know if there's any specific points you want to address, at least in magnetism for now, and I'll touch on those. But we'll otherwise go over the most, one of the bigger topics that we did at first, which is forces acting on charges in a magnetic field. So let's take a look at this here. Okay, so we have this diagram which has 3 different particles in it. So this corresponds to the 3 different questions below, 21 through 23. So we have in here in this diagram, we have a magnetic field which is directed directly upwards in the diagram. 21, we want to know what is the direction of the force that acts on particle 1 in this figure. So here you have your charge, it's a negative charge. You know it's moving to the left. Here's its velocity. And you know the magnetic field direction. So here we just need to use the right-hand rule to figure that out. So I'll try to make it a little bit more clear how you would precisely figure this out without messing around with your arm too much to get the answer. So this is what I guess this is what he was attempting to do in class, but it's kind of harder to see in the lecture. So I have my magnetic field, and it's directed directly upwards. Okay. Let me just draw this a little space here. We have a negative charge. Okay. And we know it's moving to the left in the picture with a velocity v. Okay. So what we're going to do is I'm going to go over both of the right-hand rules, so whatever makes you happy, use it. There are pros and cons to both right-hand rules, so you'll find that one will have an advantage in some places and the other one will have advantages in other places. So I'm going to start with the one where you keep your index, your middle finger, and your thumb all perpendicular to each other by default. So it kind of makes like this little corner of a room, basically. So it's all perpendicular to each other. Okay. So remember that the index finger is the velocity, the middle finger is the magnetic field, and the thumb is the magnetic force that the charge feels. Okay? So now you have two options. Remember that if it's a negative charge, it has to be the opposite of what your answer is with your right hand. So if you use the right hand with the right hand rule, you have to flip the answer for a negative charge. The other option you have is just use your left hand instead of that. I personally like just using my left hand so I don't have to flip it, remember to flip it. So what I'm going to do is I'm going to do it with my left hand. If you want to do it with your right, just flip your answer. So what we're going to do is start with the things that we know. We know the velocity, so I'm going to first point in the velocity. So the velocity has to go that way. Okay? So we point in the direction of the velocity. We need to somehow turn our hand around so that the middle finger aligns with the direction of the magnetic field while keeping the index in the direction of the velocity. So you can turn it like this, and that will not change your velocity. Okay? So if we were to turn it up like this, we have our index finger to the left, we have the middle finger up in the direction of the magnetic field, and therefore the force, which is the thumb, points out of the page. Now because it's my left hand, that's already the answer. If you're doing it with your right hand, you're going to find that it's into the page, which you then flip to out of the page. So the force, we state, is out of the page. You can indicate that by drawing a dot to indicate it's out of the page. So force out of page. Okay, so that's it. Now, if you were to do this with the curling method, which is the one I actually prefer, what you do is you keep your fingers perpendicular, so at a right angle to your thumb. You point your fingers in the direction of that velocity, so that's to the left. Okay, you will face your palm into the direction of the magnetic field. So notice how I have my fingers out to the left in the direction of the velocity. Notice my palm faces upwards into the magnetic field, so that when you curl your fingers, 90 degrees in this case, notice how it curls into the direction of the magnetic field, which is up. Okay? If that's the case, when you go from velocity that way, you curl it up into the magnetic field, which is which way your palm is facing. The thumb points out of the page, at least with your left hand. So if it's your right hand, you'll flip the answer to out of the page. So you still achieve the same result. The pro to using the curling method is that you can work with any angle. It doesn't have to be a right angle. A lot of these are right angles, but this works for any angle very easily. The other one you have to kind of bend around a little bit, which is not so great. So anyway, that's that one. For 22, we're going to consider the charge in the middle of the diagram, which we have our magnetic field upward. And we have a charged particle, it's positive, and we say that there's no force on it. Okay. Real quick here, the answer is 0 for whatever we're going to talk about, because if we have, well, actually, sorry, not going to be 0. It depends on what we're talking about. So if we have the velocity going perpendicular to the magnetic field, we do feel a force. If we have a velocity which goes parallel to the magnetic field, or if we have no velocity, that's what I meant, you would have a force being 0. So if we ask in question 22 here, what is a possible direction that particle 2 could be moving in for the figure above? Technically, there are 2 answers to that. It could either move upwards along with the magnetic field, or it could move downwards against the magnetic field. Either way would be parallel or anti-parallel, and as long as you're following that field line, there's no force. Okay. Now for the last one here, we have particle 3. It is deflected, in other words, the path steers out of the page. So what you'll notice here is that the particle on the right here, it's initially going to the left in the diagram with a velocity v, but what we're going to say is it's going to start turning so that its direction starts coming out towards you, out of the page, so it kind of just steers out of the page. I want to know what charge could it be. We don't know what kind of charges, so how would we know? So this one's a tricky one, because usually we deal with the directions of things. We just say, oh, velocity, magnetic field, and force. But there's technically a fourth thing. That's the charge, and we never really think too much about it. But I can then ask you, what's the charge going to be? So we can actually relatively easily figure that out by realizing that, okay, whatever this charge is, we know the direction it's being deflected. So notice how if it's initially moving to the left, we said it's deflected out of the page. So something is causing it to steer out of the page like this. Okay. What that means is that there's a force out of the page. Okay. So the force is out of the page. And that's not because of the right-hand rule. It's because we know the direction it's being deflected. If you're being steered out of the page, the force is out of the page. If you're being steered to the right or to the left, the force is to the right or to the left. The force just causes the change in the direction. So we know the force is out of the page, we know the magnetic field is up, and we know the initial velocity is to the left. We actually have all 3 vectors. So all you have to do is match the correct hand to the correct arrangement of vectors. So in other words, let's just say I try this with my right hand. I assume it's going to be a positive charge. So let's try with my right hand. I'll do this right hand rule. Okay, so I have the velocity is my index, so it goes to the left. My magnetic field points upwards, so I have my middle finger up. My thumb ends up going into the page, but that's contradictory because I said it was going to be out of the page. So if that's not correct, well then it has to be my left hand or a negative charge, because then for a negative charge, the answer would be force out of the page. That's the only way it will match this. So therefore, left hand or negative charge rule matches. Okay, so because of this, we therefore say it's a negative charge. Okay. So that's an interesting one. So let me know if there's any more questions on magnetism, and let's wrap this up. Any more questions on magnetism, and let's just say any more questions in general before we call it a night here. Any topics you want to quickly ask about, anything? give it about another 30 to 60 seconds. What times are the review tomorrow again, and in what room? Okay. Check on, so the announcement that you got either in your email or on Canvas, just read through that again. It's I listed it as the third point, I think. It's my usual times in the same room. So go find that, and the time is going to be from 1 to 3:30. So, and that's my regular time. So every single day before class, so Monday, Wednesday, 1 to 3:30, you'll always find me in that same location. So that includes the review time that we're going to do tomorrow. So what we're going to do is we're going to spend a little bit of time, I guess, generally reviewing, but I do want to cover a new version of the practice test that I'm going to put up for you tonight. So I'm going to, as soon as we end this live stream here in a couple minutes, I'm going to start working on that new version of the practice exam, and I'm going to push to get it up and posted before I go to bed tonight. So let's just say if you're a night owl, that's probably looking around, I'd say somewhere between 1 and 2 o'clock if you are a true night owl. So that's what we'll go over in person tomorrow, but the solutions will be up before tomorrow, before that time comes, so you can take a look at the solutions if you can't make it. Any other questions? We got, we'll be posting this so we can see it later. If you're asking if you can rewatch the live stream, yes, you can. So on my YouTube channel, if you go into the videos section, give it a couple of hours, I would say, because YouTube processes the video. If you give it a couple of hours, the live stream will be made available to rewatch. So if you want to rewatch all of this, you can do that definitely by tomorrow morning. If you're talking about the practice test, that will definitely be up as well. I'll post that to Canvas. That was amazing. Thank you. You're welcome. I could very briefly go over Kirchhoff's law. I'll just briefly mention a couple things with that. And then I'll probably do more in the review session tomorrow. So if you intend to come tomorrow, I'll do more with that. I'll put it on the practice exam. So question in general, there are formulas in the book that aren't on the formula sheet. Does he expect us to know them? Largely no, because the formulas that we give you on the formula sheet are the expectations that we have. These are formulas that we've covered. So even the most basic ones, like the definition of capacitance is charge over potential difference. It's a very simple formula. That'll be on there. All your constants will be on there. So the only things that will not be on there are things that we expect you to know conceptually. So we're not going to outright tell you things you should know conceptually in words. But formulas, sure. You will be set with your formula sheet. I'll tell you that. All right. So one last little touch-up that I'll make before we end it. I'll just spend a minute or two on this before we end it. It's just the Kirchhoff's rules. I do want to mention the most important idea behind it. You're not going to need to worry too much about it because it's not a major point that we're making in this class. But let me mention the most important things that you definitely want to take away from it so that when you have to use it, you know exactly what to do with it. Okay. What I want you to remember for the Kirchhoff's rules, is it with two H's or I forgot, whatever. I swear it's two H's. So we have the loop rule and we have the junction rule. Okay. You kind of already know these rules to some extent, and by that what I mean is we've already used them without even, naming these off. So for instance, the junction rule we've already used before without even calling it the junction rule. We would say that, for the junction rule, the most important thing is that when you have a junction or a point in which currents will split or join back together, let's just say in this case it's a split, whatever current you have going into it equals the current that you have coming out of it. So in other words, let's say in this diagram, it would be I1 equals I2 plus I3. The combination of the things that split away will add up into the thing that originally made it up, or if you want to see it this way, is when it goes through a circuit, let's say it goes through a parallel combination of things and it joins back together, the two currents will join back together into the original current. So then you get that I2 plus I3 joins into I1. So it's very straightforward. The loop rule that I want to really emphasize its usage is that when you go through a circuit, okay, the most important things are how to handle batteries and how to handle resistors. Okay, so there's a couple of things here. Number one, okay, when you cross over a battery, okay, so given that you pick a starting point, so establish a starting point, okay, that starting point could be anywhere. I usually default it to the top of the battery. Say we start here. Choose a direction you're going to walk it in. Okay, so let's say I choose to go clockwise. Okay, I could go counterclockwise, I could go clockwise, it doesn't really matter. Let's say I go clockwise. So I follow this, okay, I don't run into anything, so I don't write anything. So the first thing that you write is when you cross the resistor. When you do the resistors, a couple of things. If you go with the current, you subtract. If you go against the current, you add. So that's the other thing you need to assume, is you need to assume a direction for the current if it's not already given to you. So let's say I don't tell you which way the current's flowing in here. Well, I just assume a direction and I work with it. The worst that happens is you get a negative in your answer, and that just means it flows in the opposite direction from what you assumed. So it doesn't really hurt you to just assume a direction. So let's just say you assume it goes clockwise, okay? That's the direction of the current that's assumed, okay? So here's your current direction, and here's the direction you choose to walk it in. If you go with the current across a resistor, you will subtract a voltage. In other words, you subtract IR in your loop rule. So when you go across this, it's minus I times R, okay? I1, R1. The battery does not follow this rule, so do not do this for the battery. The battery, you know one end is negative and one end is positive, so that indicates low potential, high potential. So when you walk this circuit and you walk across the battery to get back to where you started, you will go from a place of low potential to a place of high potential. So that means you are increasing the voltage when you walk across it. So you add the voltage of the battery. And then when you return back to where you start, it means it's equal to 0. Okay? So resistors follow that rule if you go with or against the current. Batteries do not care about the current direction. Batteries, it matters which way do you go, minus to plus or plus to minus. Nothing to do with the current. Okay? So that's all I wanted to mention with that. So, that's it. I think that's it. So, yeah, if you can make it tomorrow from 1 to 3:30, then we will go over the other practice test version I'll make, but I'll definitely put it up for you tonight. And with that, I wish you the best with all your studies. So thank you for tuning in. And yeah, I'm continuing to build my website. If you've visited my website and you've kind of strolled around, I'm still piecing things together. So unfortunately, I didn't get up as much video content as I wanted to. But my plan here on out is that with each week of class, I'm going to put up new content onto that website under each respective topic. So if we cover more magnetism, I'll put up some magnetism videos for you if it helps you. So hopefully that helps you out. But thank you for tuning in and have a good night.